Hello, this is lecture 6, probability part 1. Today we are going to cover the probability, or at least introduce the probability. And probability, as we said, we needed to go from the sample to the population. In other words, we want to generalize whatever we did find in the sample to the population, which is meaning making inferential statistics. To be able to do that, we need to study some rules in probability. Now, what is probability after all? Probability is the chance of an event occurring. And what is the event? Event, this is a set which consists of outcomes from a probability experiment. So what is the outcomes? From where can these outcomes come from? These are the results of a single trial of a probability experiment. So what is a probability experiment then? The probability experiment actually is a chance process that leads to well-defined results called outcomes. Like what? Like rolling a die, one die. The well-defined outcomes are number from 1 to 6, or drawing a card from the standard deck. The well-defined result of this probability experiment is any card that could have a number from 1 to 10 with two colors, one either black or red, and also having one shape of the four known shapes in the decks. Now, another concept that we will use is the sample space. What is the sample space? The sample space S is a set of all possible outcomes of a probability experiment. Like going back to the rolling one die experiment, so the sample space is all the numbers from 1 to 6. Now, the event which we did define as a set of outcomes, it can have two forms. Either having in it just one outcome of my experiment, and in this case we're gonna call it a simple event. Or it could have more than one outcome, and in this case it's called compound event. Example for the first one, rolling a die, and you did define your event as being obtaining a 3 when you roll a die. This is just one outcome from the 6 outcomes in the S. For the more than one compound event, I can define, if I did define actually my event to be obtaining an odd number, here you are gonna see that odd number means 1, 3, and 5. So I do have 3 outcomes from my 6 outcomes. So this is a compound event. So what are the sample space for the following experiment? Flipping a fair coin. It's either tails or heads. So this is the sample space, having all the possible outcomes for this specific experiment. Rolling a fair die. This is what we said, the numbers from 1 to 6. These are all the outcomes that could appear if you really did go ahead and roll a fair die. Flipping two fair coins. Well, two fair coins, it means I will have a result on the first coin and another result for the second coin. Because of that, I could have heads and heads, heads and tail, first coin and second coin, or tail on the first and head on the second, or on my both coins, they will show tails. Now here, what is the sample space S for rolling two dice? Well, again, I will have here two, not coins, two dice, and for each one of them, I will have faces from 1 to 6. So if I'm gonna roll two dice, I could have on my first die the number 1, and on my second the number 1, or I could have 1 and 6. So all the possible numbers here, all the combinations in that table, first number representing the first number or the number on my first die. The second would be the number that will show on my second die in my experiment rolling 2 dice. So all of these combinations of my 6 numbers are representing the outcomes in my S. So I can now write the sample space as first outcome, second outcome, and so on till the 36 outcome. Why 36 outcomes? Because I do have here exactly 36 inner cells in my possible table here, in showing all my possible outcomes. How to calculate probabilities for any event? We do have 3 types of probabilities, or 3 approaches to probability: classical probability, subjective probability, and empirical. Sometimes we call it also frequency probability. So any probability we will have, it's gonna come from any one of these types. Okay, let's begin with the subjective probability. The subjective probability, it's based only on an educated guess or an estimate from an expert in the field. Like, for example, an expert can come and tell you that there is a 10% chance that it will rain today. So from where did he or she know that? He is an expert or she is an expert in that field and are able to quantify the chance of having rain today. A classical probability depends on the sample space S, and we are assuming in this approach that we do have equally likely events. So any event is having the same probability to occur. And the probability rule in this case would be the probability of the event E to occur is nothing but the number of outcomes in my S that are satisfying this specific event over the total number of outcomes in S. And here we don't need actually to perform the experiment itself, because we know we can list on a piece of paper how many elements do we have in my sample space, or write all these exact outcomes in my S. And from those, I can count how many among them are specified or are related to the event of interest. The last approach is the empirical probability or frequency probability. This depends actually on a frequency table, and here we need to run the experiment so that we can get the frequency distribution table, and from the frequency distribution table we will be able to know the frequency of each class, which will be here in terms of probability, mean the probability of each event, the frequency of each event over the total number of the frequency in your table. So it's F over N, F frequency for a specific class or event, N is the frequency of the total. And if you remember, this is nothing but the relative frequency that we did calculate before. As you see here, I do have here approximately the probability or the chance of event E occurring is approximate equal to the relative frequency. And as we said, we need here to perform the experiment such that we can know F and the total frequency. And here, that approximation idea, the law of large numbers is saying that as the number of total frequency N increases, you are gonna approach the theoretical probability, which in some cases could be the classical probability. So the rules for probabilities, any probability would be between 0 and 1 inclusively. The sum of all the probability for all the outcomes in a sample space S has to sum up to 1. If an event cannot occur, then definitely its probability is equal to 0. And in this case, you are going to call that event impossible event. On the other hand, if an event is for sure it's going to appear, we call it a certain event, and its probability would be 1. Now, an example for an impossible event is rolling a die and defining your event to be getting the number 7. Well, number 7 will never appear if you are rolling a die, so it's an impossible event with a probability equal to 0. But if you define your event to be having a number less than 7 and greater than 0, this is a certain event because all the outcomes in my S for this experiment, which is in this case rolling a die, are numbers between 1 and 7, numbers from 1 to 6. Now, when you are gonna calculate the probability, you could round it using just 3 decimal places, so keep 3 decimal places, or report the reduced fraction. So let's consider this new example, rolling 2 dice, and we want to know what is the probability that the sum of my 2 faces or 2 dice is being 8. We have here the sample space, and I do have our 36 outcomes in my sample space for this specific experiment. We did talk about that sample space before, and we want to calculate the probability of that event, the sum being 8, occurring. So all what we need to do is to go ahead and calculate the probability using any approach of or the suitable approach from our 3 different approaches. Here I do have equally likely events, so classical approach is my approach to calculate this probability. So let me go ahead and see how many of these 36 outcomes are related to my event. So 2 and 6 are 8, 3 and 5 is equal to 8, 4 and 4, 5 and 3 is equal to 8, and 6 and 2 is equal to 8. So all of these 5 outcomes are actually outcomes that satisfy this event. Their sum is equal to 8. So now I know the numerator of my probability for this specific event, and I know also n of s. This is how many total outcomes are there in my sample space. These are 36, which means now that the probability of this specific event, sum is equal to 8, is having in its numerator 5 over the 36, so it is that probability. The second one, what is the probability of the sum of the 2 dice being greater than 10? We are going to use the same idea here. We are still in equally likely events, and we want to know the probability of greater than 10. So how many of these 36 outcomes is going to have a sum greater than 10? Well, obviously 6 and 6. 5 and 6, 5 on my first die and 6 on the second, and 6 and 5. So only these 3 outcomes are gonna have a sum which is greater than 10. So it's 3 out of 36. And 3 out of 36, this is not the reduced fraction, so I can go ahead and report 1 over 12. Complementary events. The complement of an event. What is this? The complement of an event E is the set of outcomes in the sample spaces that are not included in the outcomes of that event. So they are not defining the event E. And we are going to use E bar to represent it. So the complement of an event E is E bar. Sometimes also we call it E prime or EC for complement. Okay. Now, to represent that on the Venn diagram, usually in the Venn diagram, we are gonna represent the whole S by a rectangle like this. And inside it, we are gonna have an event, usually represented by an oval like that. And this is event E, so I'm gonna call it E here. So the complement of event E, by definition, is any other outcome in that rectangle, in that space S, but not inside that oval or that circle E. And which means this blue area is your complement. And since we do know that there is a rule which is saying P of S, the sum of all the probability inside the same S is equal to 1, which is the whole rectangle. This means that the probability of E bar plus the probability of E is equal to 1, which means that the probability of E bar is nothing but 1 minus the probability of E. So let we see some examples here. What is the complement of the event E, the sum of the dice faces greater than 8? This is actually E bar, which is the sum is less than or equal to 8. What is the complement of selecting a letter of the alphabet and getting a vowel? So it's if E is selecting a vowel, then E bar, its complement would be selecting any other letter but a vowel, or any letter but a vowel. What is the complement of selecting a month and getting a month that begins with the letter G? So the complement of selecting a month and getting a month that begins with a letter G, this is actually the E. So the E bar would be any other month, but not one of these that are constituting our event E. Mutually exclusive events. When are two events mutually exclusive? These events, the mutually exclusive events, are events that cannot occur together. So if one is occurring, the other one is not gonna occur at all. These events are usually called disjoint events. Now on the Venn diagram, this is again our S, and on the Venn diagram, A and B, if they are not intersected at all, so this is event A and this is event B, they don't have any common area between them, they are not intersecting at all. This means these are mutually exclusive. Again, mutually exclusive events sometimes are called disjoint event. So let me see some examples here. Determine which events are mutually exclusive. Selecting a cell phone plan with event which includes unlimited talk and unlimited text. Well, to answer that, we should ask ourselves, could these two events, unlimited talk and unlimited text, occur together or not? Could these two events happen together or not? So in this case, they could happen together, so they are not mutually exclusive. Randomly selecting a female student and randomly selecting a student who is a junior. So female student is first element, a first event, and the second one is a student who is junior. Could these happen together? Yes, because a female student could be a junior, so these are not mutually exclusive. Randomly selecting a person with type A blood and randomly selecting a person with type O blood. So first event, type A blood, second one, type O blood. Could these happen together? The same person could be having type A blood and type O blood? No. So these are mutually exclusive, because if that person is having A, he will or she will never have blood type O. So second example, or the next example, rolling a die and getting an odd number and rolling a die and getting a number less than 3. So again, ask yourself, is getting a odd number, could it be Less than 3? Well, yes, because less than 3 numbers are 1 and 2, and 1 is odd, so these two events could happen together, so they are not mutually exclusive. Randomly selecting a person who is under 21 years old and randomly selecting a person who is over 30. So the person be under 21 and over 30 at the same time? No, so these are mutually exclusive. So let we take other concepts, the intersection and the union of two events, and see how to represent it on Venn diagram. So the intersection between two events A and B means that these events are happening together. So event A and event B are happening together. The probability of the intersection means the probability of these two events occurring at the same time. And notation wise, we are gonna talk about that like intersection A and uppercase U upside down B. This is the intersection sample A and B. So P, the probability of the intersection. On the Venn diagram, if this is the Venn diagram now, and A and B are these two ovals, then the intersection area is the area that if you are in it, it means you are in A and B at the same time. And this is that area, the common area between them. Now, the probability of the union of two events. The probability of the union of two events is the probability of the event A or B. So you are either in A or in B or both of them. So, and we are gonna notation wise talk about probability of A or B. Notation wise, it's gonna be probability of A, uppercase U, B. So this U, uppercase U, is OR and it stands for union, while this uppercase upside down U is standing for the intersection. On the Venn diagram, since it's A, you are either in that A or in that B or in the intersection, so it's the whole area. Now, the addition rule is saying that calculating the probability of the union is known in probability by the addition rule, and it is calculated as the probability of A plus the probability of B minus the intersection. So it's like, what is the probability of that A plus the probability of B, but I need to subtract intersection. Why is that? Let we see from where did that idea come from. So I have A, the probability of A is that whole area, or that whole probability, notation wise of course, and the probability of B would be that one. As you see here, I did add the intersection twice. That area is gonna be added twice if I am saying probability of A, which is that one, plus probability of B, which is that one. So I did add that twice. I need to take one of these so that I'm gonna have that area with only one common shared area in between. Now, if I have A and B, I know that these are mutually exclusive, disjoint, then their intersection probability is equal to 0. Why is that? Because as we said, the intersection is a common area between two events. If these are originally, or we begin with two mutually exclusive events, we don't have any common area. And so the probability is exactly equal to 0. So let we see that example. We do have the distribution table for the number of days stayed for 127 patient who did undergo a knee replacement, and we want to find the following probability. A patient stayed exactly 5 days. So what is the probability that the number of days is exactly 5? According to my frequency distribution here, I do have 56 one out of my 127 who stayed exactly 5 days, which means I can use the frequency approach to probability, or the empirical approach to probability, which means the probability of 5 is exactly 56 over 127. The probability of a patient stayed fewer than 6 days, well, 5, 4, and 3. So the probability of a patient stayed fewer than 6 would be that or that or that. So I want the union of these three options, or these three events, and these are mutually exclusive. So it's just nothing but the addition of, according to the union of the events principle, it's the addition of the 15 plus the 32 plus the 56 over 127, giving me that number. So again, what is the probability of a patient stayed at most 4 days? Here is our table again. So at most 4 days, it means 4 or less. So 3 plus 4, again, these are disjoint events. So the probability of either stayed 4 or 3, union of these would be the sum of each one of the probability 15 over 127, the probability of 3, and the probability of 4, which would be 32 over the 127, again using the frequency approach to probability. A patient stayed at least 5 days. At least 5 means 5 or more. So 5, 6, or 7, summing or adding all of these together and dividing over 127 will give me the probability of a patient stayed at least 5 days. So this is the end of our lecture 6. Next time, lecture 7 would be also about probability, continuing some other rules in probability, as we will see in 2 weeks.